Good morning, sir. Sir, good afternoon.
Good afternoon, ma'am.
Sir, is it audible?
Yes, ma'am.
It's audible, ma'am.
Yeah, okay, ma'am. Thank you for the invitation, sir. Good afternoon, one and all present here. I am Nesasudha, working as an associate professor in EC department, Karunya Institute of Technology. So it's a great pleasure for me to be with you, and I want to share my experience about the metamaterial in place on the antenna design. Okay, this is the content I have decided to present. Introduction, background about metamaterial, what are the properties, how we can classify it, what are the different applications of metamaterial, and I am planning to take two applications. One is related to antenna, other is related to clocking. So when we talk about material, there are different kinds of material, different status. Each material has its own characters or properties. When you take one material, this property will not change at any cost. This is the normal phenomena. Then what do you mean by metamaterial? If one can try to change the character of a material, that artificial made material, that is called as a metamaterial. So metamaterial is not, it doesn't have any natural properties. All natural materials like glass, diamond, they all have the permittivity, permeability, and refraction index. All are positive. When we try to change the character of any one of this material by making them negative, then that material is called as a metamaterial. So metamaterial is not a natural material, it is an artificial material. By changing the character, so that we can change the property of the electromagnetic waves. So only the metamaterial wave can change the electromagnetic properties. So that's all about metamaterial. So metamaterial, we must be very clear, this is not a natural material, it is the artificial material which is developed from the natural material by changing the character so that we can use it for our electromagnetic applications. So when I take the metamaterial, here the permittivity, permeability, refraction index all are negative. Since both permeability and permittivity both are negative, it is called as a double negative material or double negative media. Also it is called as a negative index material, since the refractive index is negative. Also it follows the left hand material rule, that is the propagation is in the reverse direction. Also it is called as a backward wave. So when the material propagate in the forward direction, it is called as a forward wave media or material. Since this metamaterial has a character of propagating in the backward direction, it is called as a backward wave propagation. So when you see the classification of metamaterial, we can take this classification into 4 quadrants. So these quadrants are based on the permittivity and permeability. So in the first quadrant, both mu and epsilon are positive. Okay, this is called as a right-handed rule. So when you take any material, most of the materials, they follow this category, where epsilon is equal to, epsilon is greater than 0 and mu is also greater than 0. As per the diagram, we can say the wave will propagate in the forward direction. It is in the forward direction. Most of the materials are coming under this category. Next category is, here we can take quadrant 2 and quadrant 4. So some materials, they may have any one of the properties as positive, other may be negative. Okay, when you take this quadrant 2, it is a single negative material because one character. either here when you take here mu is greater than 0. Mu is greater than 0, but epsilon is greater than 0, less than 0. So one is negative, one is positive. So it is called as a single negative material. So some materials like this thin wires, CRR, triple wire, spiral resonator, Swiss roll structures. So these all materials falling under this category. So it is called as a single negative material. The third, this fourth category, this is also called as a single negative material. Here also, any one property, that is here mu is less than 0 and epsilon is greater than 0. So this is called as a single negative material. Here the best example is ferrite material. So by nature itself, very few materials like ferrite, they have the single negative materials. Remaining all materials are coming under the first category where both are positive and the direction of propagation is in the forward direction. So now one more quadrant, that is the third quadrant. So in this quadrant, both epsilon and mu, both are negative. Both are negative. Here the direction of propagation is in the backward. So it is called as, it follows the left-hand rule. When both are positive, it follows right-handed rule, where the propagation of wave is forward direction, whereas when both epsilon and mu are negative, it follows the backward propagation method, or we can call it as a left-handed rule. So that is only explained here. So material characteristics can be altered on the basis of permittivity and permeability. As shown in the first diagram, both values are greater than 0. This is a right-hand material RHM, where the direction is in the positive or forward direction. Most of the materials coming under this category. The second quadrant and the fourth quadrant, they are called as the single. Where here, when you take second quadrant, only epsilon is negative, whereas in fourth quadrant, mu is negative. So this is the second quadrant, it is called as a epsilon negative. Here, this fourth quadrant, it is called as a mu negative materials. And coming to the most important third quadrant, here both are negative. This is called as the metamaterial. So the character of, or the properties of mu and epsilon are both are negative, which makes the wave to propagate in the backward direction. So this is a negative propagation basic principles. Then in a conventional medium, when wave is made to incident between the interface of two media, it passes through the positive direction. But in this metamaterial, the wave is made to pass in the metamaterial interface or surface. It is written in the same reverse direction. Okay, this is the basic principle used. Okay, this is that's what it's called as a double negative material, because both are negative. So this was first invented by a scientist called Winston E. Koch in 1948. He first identified that there is an artificial dielectric is also possible with the help of natural material. Based on his work, many researchers have done scientist J.B. Pandre, he has done much work on the metamaterial. He has done research and published many papers in around the years of 2000. He worked on the basis of negative refractive index. So this is the different metamaterial based structures. So we must remember one thing. So metamaterial is not a new material, already existing natural material. We are making some modification, or some structures, some periodic structures are introduced in the already existing natural material, so that the material characters will change. So while changing the character, some may be coming under either mu negative or epsilon negative. Some may be forced to the third quadrant of both are negative. So when both are negative, then only we will call it as a metamaterial. So these are the some structures. So these structures are repeatedly used. So these are the structures which is repeatedly used. Here it is called as an artificial magnetic material. That is a small structure which are used to create or change the character. They are called as a AMM. These artificial magnetic materials are coming under the metamaterials. So AMM, this is a electrically small metallic broken loop. So it's not a closed loop, it is a broken loop. It is in the parallel planes, and the perpendicular to the direction of incident magnetic field. Okay, when they see this structure, this is not all places, it is some openings will be there. Opening will be there. This incident magnetic field induces the electric current. So when you take a metamaterial, there will be a small structure that is called as the AMM. AMM is the artificial magnetic material. So these are few examples of AMM. So this is there are two rings, but each ring is splitted. There is no it's not a closed loop. There is a discontinuity. So this is called as a double split ring resonator. So it's a ring. So next is a square. So there are two squares. It is called as a double split square resonators. Next is a single split. See here, though there are two rings, but split is only one split. So here there are two splits. It's a double split. But here it is a single split. When you take this, when you take the D thing, it is a two-turn circular spiral resonator. Okay, similarly here it is a two-turn square resonator. So here we have some stack. This is a Swiss roll. Okay, here it's a modified ring resonator. So these are the different structures used in the normal natural materials and making them to metamaterial. Okay, this is a metamaterial slab. So you may be asking, so these are the structures what we saw. There are different kinds of artificial structures. These structures are made over some plates. They are called plates. The plate may be some substrate, copper, FR4, or anything, any material which is available physically or some natural character over which this artificial materials or some modifications are made. So this is a typical response of a metamaterial. Okay, we'll see it more clearly after explaining this. Okay, now come to the applications. When you take metamaterial, it finds wider applications. Nowadays, see, antenna is the basic for all transmitting. Whenever the data it is processed, finally we need the antenna for transmission as well as the reception. If in later days, people are working on how to reduce the size of the antenna, how to reduce the energy dissipation, how to reduce the absorption rate. So researchers are going on how to efficiently use this antenna. So when you use this metamaterial structure inside the antenna, what are the different applications it finds? So what are the applications we can use it? Okay, I have listed many applications, but I am going to explain only the first two applications. How metamaterial is used in the antenna, and what is clocking, and what is the relation clocking and metamaterial, how this metamaterial creates an impact on clocking. Okay, apart from this, along with clocking only, we have invisible submarines and aircraft. Okay, when aircraft is there or submarine is there, everyone can able to see. But how to hide this aircraft or submarines from enemy sights or radars? How the radars, this aircraft can escape from the eyes of radars. So this, so what is the relation between this metamaterial and this invisible objects? Okay, next, photonics. in the lights, in absorbers, solar cell, super lens. So these all finds applications of metamaterial. Okay, now take the metamaterial unit and unit cell analysis. Okay, unit cell is a small portion. See here, this single structure. When you take slab or when you take any substrate, there are a number of structures. The same structure is repeated. So unit cell means only a small structure. So this structure we have to design. Actually, it is an antenna. Okay, when you take antenna, we already would have learned it morning session also. Ma'am would have explained clearly what is antenna, what are the different layers of antenna. So when you take the microstrip patch antenna, in the antenna we can have mainly 3 layers. One is the ground layer. Over the ground layer we have the substrate. Over the substrate we have the radiating element or antenna. Okay, first we have to design the antenna. Okay, now this antenna is placed under the boundary conditions. Okay, here, so this is a unit cell. Okay, this is a unit cell. It is placed inside the boundary conditions. So there are 2 ports we have taken. Okay, here it is port 1 and it is port 2, or you can here take port 1 or port 2. Okay, through port 1, we are applying the input signal. The input signal is applied to port 1. And you are checking how much amount of radiation is passed through it or transmitted and how much is reflected back. So when you measure the radiation at the same place of 1, as the same place of 1, it is called as S11. So whatever you are sending at port 1 and how much is returned back, okay, that is measured in S11. Okay. So this is S11. That is called as a reflection. So how much amount of radiation is reflected back, that is measured from the send port P11. S11. Okay, this is S11. Okay, this is S11. And how much is radiated? Say transmitting in port 1 and port 2 it is radiating. So you are checking how much amount of radiation is transmitted or radiated over port 2. Okay, that is measured in S12. So this is here, this is the S11 and S4. This is transmitting and this is the reflections. Okay, based on this, you can improve both the character. When you take the metamaterial, if you alter the character of metamaterial in such a way that you can use it for transmission purpose or you can use it for receiving purpose. Okay, receiving purpose means it will be an absorber. Okay, transmission purpose means it is a reflector. Okay, all will be reflected, sent back. Okay, when any signal is passed through the antenna, it will be returned back or it can absorb. For both purposes, we can use this metamaterial. Okay, some applications we don't want the radiation. Okay, in such case, we have to return it back. Okay, some applications like solar cell, we want to save the energy. In such case, it can be used as absorbers. So what are the challenges when you are going for metamaterial antenna design? See here, the first one is conformal or flexible antenna. It is the low profile antenna, we'll call it as. So normally when you see the antenna, flexible, that is the normal patch antenna which is used in the mobile, these all antennas are rigid. You cannot make it to bend. If you try, it will break. Okay, but some applications, suppose if you are making some antenna and you want to wear it over the dress, or you want to keep it on your watch, or if you want to keep it in the wrist and the body, so it cannot be rigid. It has to be flexible. So when you are designing this flexible antenna, how this metamaterial affects the performance. So next is that this metamaterial reduces the size, miniaturization. Can reduce the size of the antenna, cost, weight, everything can be reduced. Next one, greater challenges when using the metamaterial antenna, the bandwidth has to be improved. Okay, there may be, suppose when you are designing particular frequencies, when you are attaching the metamaterial or when you are applying the metamaterial concept, there will be a shift in the frequency, but bandwidth should be maintained. Also, you have to improve the gain. So when that is also important parameter while designing this antenna with metamaterial. Operating frequency tuning, reconfigurable. Okay, now many people are working on reconfigurable antenna, which is used for 5G applications. In reconfigurability also, this metamaterial antenna is used. Also for memo, to avoid the isolation, that is separations, to improve the separation, this metamaterial can be used. So when you see this is a structure of metamaterial as a plane. Okay. See here, this is one structure. This is a repeated structure which is placed over a known material. It may be any substrate. Okay, take this structure, this is called as a small structure. That's artificial AMM, magnetic material. So this is on this hexagon shape. So this structure is corresponding to a electrical circuit. Okay, these all are called as a strip line. Okay, those who have done the simulations, you must know this. Okay, these are the strip lines. So you may be asking, what is the relation between this metamaterial structure and the strip lines? So this structure is connected to the electrical lump parameters. So here, so this is a parallel line. So this is a parallel plate of this hexagon. This is a parallel plate of this hexagon. So this two acts as a capacitor. Okay, it is a capacitor, and this vertical. Okay, here this is vertical. This is vertical. Okay, this is a capacitor. This is the gap between the two parallel plates. It acts as a capacitor. This vertical lines, these are the inductors. Okay, this is placed over the substrate. Under the substrate, all are connected together. Okay, this is a ground plane. So this ground plane, since all are connected together, that is a resistance. Okay, this is replaced like this. So this vertical line, this vertical line is similar to this vertical line. This is represented by a inductor. This parallel plate capacitance space, this gap is represented by the capacitor. Okay. So this structure is continued. This is repeated. Now where comes the resistor? So here, please note it down. This is not inductor. This is a resistor structure. This is a resistor structure where all the small units are connected in the ground plane. So I said ground antenna has three planes. First is a ground plane, substrate, and radiating element. In the substrate here, all the arrangements have been made, and the normal natural substrate is now converted into metamaterial substrate. Now substrate is this all elements are connected in the ground. That is the resistance. So when you take our frequency, F is equal to 1 by 2 pi LC. Okay, when you change any character of this L and C, you can be able to change the frequency. Okay, this structure may differ from metamaterial sheets to another sheets. Okay, this is another example of metamaterial to improve the gain. Here, say this is these are the repeated structure, metamaterial structure. So here they have given the LHM. Okay, it follows the left-hand rule. So where both mu and epsilon both are negative. So here this is a patch antenna which operates in 2.4 gigahertz. Okay, this is the side view they have given for the to indicate the number of metamaterial sheets. So this is the radiation pattern. This is the E plane. So when we see the radiation pattern, you can see the difference between normal patch antenna and this patch antenna. Okay, you know this radiation pattern. This radiates in the forward direction. It radiates in the forward direction because of the metamaterial. Okay. So these radiations are absorbed in the metamaterial, and the gain is improved. The gain can be improved. This is for the H plane. So this is an example. Okay, when you take the basic antenna, so when you take any antenna, the reflector can shift the energy with zero phase shift, but the condition is it must have quarter wavelength. Okay, the distance between this antenna and the conductor, the minimum distance is λ/4 spacing. That is a 1/4 wavelength is must. So also the wave may be destructive or constructive. So destructive means if all the waves are reflected back, both will be added together and the radiation will be more. That is the constructive. So destructive means some will be refracted, some will be reflected. So the amount of radiation will be less. Okay. When you are applying this metamaterial periodic structure, see the difference. Here, this is in the previous case, it's a normal conductor, normal substrate, a normal conductor. Here, it is a metamaterial based, it may be conductor or it may be a substrate. When you place the antenna, this spacing is not needed. So even it is lesser than λ/4, still you will get a radiation. Also here the constructive interference. If there is no absorption, everyone is reflected back, the total amount of reflected wave will be the additive wave. So I want to give some case studies what I have done it. Okay, this is a small antenna which is designed, the dimension shown, and this antenna is subject to the boundary conditions, and check for this S11 and S21 values. See here. So this is the transmitted one. This is the reflected one. Okay. So this see here. See the boundary conditions. So transmitter from port 1 already I explained you. So when you take any metamaterial, any antenna, first you have to check. See, you can take the natural material. We can say modification in the natural material property, but how to check whether it is a single changed or double changed, whether mu alone is changed or epsilon alone is changed or both are changed. So first, once you design the antenna, first you have to check whether it follows the metamaterial property. Okay, that is called as a unit cell analysis, whether you are getting both or negative values. So this is a case study I have taken. So how to calculate n value, z value, mu value, and you have to check all the values are negative or not. Okay, this is S11, S21 we can calculate from that previous diagram. What is the S11, how much is reflected, how much is transmitted. From this you can calculate the impedance Z. Applying this, you can calculate what is n value. With the help of Z and n, you can calculate epsilon. Okay, next, with the help of n and Z, we can calculate mu. So with these formulas, with the help of MATLAB, you cannot do it by simply applying. For every position, you have to take it. With the help of MATLAB, you can calculate n and n, epsilon and mu. That is refractive index, permittivity and permeability. So what's the condition for metamaterial? All these three must be negative. Okay, when all these three values are negative, then only we can say material is a metamaterial. Then only we can go for further process. So once the antenna is designed, next we have to analyze this. So see this diagram. So now we know what is n, what is mu, what is epsilon. We have to analyze all this with the help of frequency. See the first diagram. This diagram, this n is real refractive index and impedance, real value of N and impedance. See, both are compared. Okay, so here this N is this one, this dotted line. The dotted line is a N. So N here it is coming negative. Okay, we are not checking the impedance. We want only N. So here N is negative. Next we are taking the imaginary refractive index and impedance. Here also it is almost nearing 0. It is the negative. It's for 2.4 gigahertz. The frequency is 2.4 gigahertz. So it is also negative. So from these two graphs, we can say that refractive index is negative. Next, you have to calculate the permittivity and permeability with respect to frequency. Okay, so this is a dotted line. So when you take the permittivity and permeability in the real, see here it is, see here it is nearly 0. Okay, this for this antenna design, getting 0, nearly 0. Here it is less than 0. So when you take this point, it is less than 0. So from after analyzing this, after testing the particular single cell, I can say now this cell coming under the metamaterial property. Okay, then I can go for further steps. So as usual, first we have to design the normal antenna. Then we have to put it in the analysis, unit cell analysis, to find whether this unit cell follows the metamaterial property. If it follows, then I can go for the further steps. Okay, this is a metamaterial based reconfigurable antenna. This is antenna we designed in the lab. Okay, here, so this is a reconfigurability. Here it is the diode, pin diode we used for switching. Here in the bottom we have the Z on a shape like Z. So this Z is a ground plane is also this shape, Z shape, and the radiating element is also Z shaped. This blue color, this is a Roger material. In this material, this is the structure. Okay, this is a metamaterial structure. So this structure only I have shown earlier first. So this is the structure. Unit cell. This is a unit cell. This repeated structure or repeated unit cell, this forms a metamaterial. Okay, now this is a metamaterial antenna. So now I can say this is a metamaterial based antenna because it follows the character. What is the character? What's the property of metamaterial? It is refractive index is negative, mu is negative, epsilon is also negative. Okay. Now this metamaterial is embedded inside the antenna. Okay, here when so there is a mutual coupling between this antenna when the radiation is given, when the antenna receives the radiation when the switch is, the diode is, the pin diode is used for switching here. Based on the switching, the radiation pattern, everything is same. It will change. Here it is, when you take S1 and S2, both are S1 and S5 are symmetrical. S8, S4 are symmetrical, S2, S6 are symmetrical, S3, S7s are symmetrical. Okay, since we are concentrating on the metamaterial, okay, I have given only this, how this metamaterial is embedded. Suppose if you want to know more about how this reconfigurability is taking place, this paper is published in RF microwave journal. Okay, you can refer it. That is the switching, full operation switching sequences, how to turn on, turn off the diode, all the details we have given very clearly. So for the sake of metamaterial embedded, I have taken only the configurations. So this is how the radiation patterns, okay, how it is when the S1 is on. When you see here S1 on, we are getting S1 and S5. S5 is almost similar, and when you take S2 and S6, when you take S2 and S6, see here you can find the similarity since both are identical. So, okay, our next one is metamaterial can be used for miniaturization also. So miniaturization, so nowadays people are working on this. So there's always a inverse relationship between the size of the antenna and the frequency. When size is more, it operates in low frequency. Now people are working in millimeter waves and very high frequencies. So automatically the size of the antenna should be less. Okay, for miniaturization also, this metamaterial, this concept is used to reduce the size of the antenna. This is one of the antenna what we designed. Okay, now metamaterial antenna find wide application in medical field, medical antennas. Okay, knowingly or unknowingly, every day we are dealing with medical antenna in our day-to-day life. So when we are holding the mobile phones, a mobile phone has an antenna. It has a radiation. So this radiation affects the human body. It is related to the medical issues or health issues of a human body. So while designing such kind of antenna for medical applications or some mobile application where human held antennas, human are using, in such cases, the major problem is we have to reduce the radiation effect. Okay, that's a standard recommended value for SAR. Specific absorption rate, it must be less than 1.6. Okay, this is a recommended value. So whoever using the mobile phones or anything, a SAR value must be less than 1.6 watts per kg. This is a recommended value. So now people are working how to reduce the SAR value less than 1.6. So one remedy is metamaterial. When you apply metamaterial concept to this kind of antenna, so definitely your SAR value, you can bring it down. People who are working on this SAR analysis or medical analysis, you can apply this concept. Apply this metamaterial in your antenna and check the SAR. Okay, definitely the SAR value is getting reduced. We'll see how it is. So this is an antenna we designed. See here the overall structure is given. The bottom layer, it is a copper. It's a ground plane, it is a copper. And over the copper, there is a term called PDMS. PDMS stands for polydimethyl siloxane. Okay, this is normally when you are doing any antenna, we used to take the substrate at FR4 or Roger, okay, which is commonly available. But this kind of substrate is not suitable or not fit for biomedical applications. Okay, when you want to keep it in your body, in your chest, on your hand or thigh or stomach or anywhere, you cannot place it rigid. It must be flexible. When you are wearing the coat, the antenna must be bended. It must be flexible. So normal rigid antennas are not used for this kind of applications. So we have developed a PDMS. So if you want to know the development of PDMS, I'll explain at the end of the session, how to create a flexible substrate. I'll explain later. Now take itself like the PDMS stands for polydimethyl siloxane. Okay, this is the chemical combination we can create the substrate. Now this is a ground plane. So this gray color, this is a PDMS. Over the PDMS, so you can say easily these are the repeated structure of metamaterials. So this is a unit cell. The same cell is repeated structure. So this PDMS is now changed to a metamaterial PDMS. So over the ground plane, this PDMS is placed. See the diagram. Over the PDMS, you can see this is a blue color. Right? Okay, this is a blue color. This is a jeans cloth. Okay, this is a jeans cloth. Dielectric, this is a jeans cloth. So over the jeans cloth, here this you have the antenna. This is a radiating element. Okay, when you see, this is a ground plane. Over the ground plane, we have a metamaterial. Over the metamaterial, we have a jeans. Over the jeans, we have the antenna, a radiating element. So there are 4 layers are there. 4 layers are there. So here jeans, you can stitch it over the dress. You can so when antenna is always in your body, how much we must be careful to reduce the radiation, because our body should not be subject to high radiation. It must be less. That's why this metamaterial is placed between this ground and the jeans. So what will happen is, so here this radiation is this substrate, this antenna, radiating element. This is the radiation. Not pass through here. It is the coming to this metamaterial PDMS based substrate. Now, what metamaterial will do? No, it will absorb the radiations. It will absorb the radiation and it will return back. It will not give it to the body. So, radiation which may cause the body and increase your SAR is drastically reduced because of the metamaterial. So, the metamaterial it is bridge between our human body and the antenna. So, the absorption or radiations coming towards the body is protected by the metamaterial. This is another antenna. See here, when you are using this kind of flexible material, here also we have used only PDMS. It's a flexible structure. So when you are using the flexible structure, you can bend the antenna as you like. Okay, when you bend also, it will not break. Also, but when you are bending, some the frequency shift will be there. Because of that, there is a bandwidth changes there. Loading effect. So when you loading effect means human body character should not affect the antenna. That is that in that way also this metamaterial helps. So it's act as a protecting layer for radiation to the body. Similarly, body's loading effect should not affect the antenna. Instead, that case also it is useful. Okay, this is another antenna. Okay, how it is measured. Okay, after as I said, sir, after analysis, NMS is no metamaterial substrate. It is with metamaterial substrate. Without metamaterial substrate, this is you're getting the exact frequency. But with the help of metamaterial, there is a shift in the frequency. But there's no change in the bandwidth. Bandwidth remains same, but there is a shift. The metamaterial changes the shift in the frequency. So when you're designing the antenna, you must take care of tuning the frequency also. Okay, they're the same thing. It is the yes, sir. Yes, sir.
Ma'am, your presentation is not visible, ma'am. It is
not visible,
changed.
Sir. Everyone. Hello, sir.
Alex,
sir. Sir, can you pin? In my name, there is a pin option. Is there? Can you pin and check it? Sir, Alan, sir.
Yes, it's visible, ma'am. It's visible, ma'am. No issues. I think maybe he need to pin your window.
Okay, sir.
Sir, please try Mrs. Nesasudha ma'am's pin window so that it will be visible.
So Nikki, there is a pin option. Is there? If you press the pin, it will be visible, sir. Hello. Sir, shall I proceed?
Yes, ma'am. You can proceed, ma'am. Please.
Is it audible?
It's perfectly audible, ma'am.
Okay, okay, sir. Thank you. Okay, see this same. So this antenna, one antenna with the same without metamaterial. It is with metamaterials, so we can find the frequency shift. So whatever I have explained about SAR analysis, so we have to apply this metamaterial concept to reduce the SAR. So after design the antenna, first we have designed the antenna, we check the antenna follows the metamaterial characters. After that, we applied with different layers, fabricated, we tested, we measured. Then we check for the final SAR analysis. Okay, we place the antenna over the human body. So in this example, we placed in the hand. Okay, in other antenna, some places we placed in the shoulders, then chest, stomach, thighs, whatever the position we want, we can place. So the antennas are flexible, so you can place anywhere. And we check the SAR analysis. Say without this, it was 1.3. Okay, with the help of metamaterial and bended, it is reduced to 0.43. Okay, see how much amount of reduction in the SAR. Also, it is bending. Okay, so when there is a flat, the gap between the antenna and the body will be more. When you bend, the gap is less, because when you bend, it will not be straight, it is flexible. So gap will be less. Even then, see here, the SAR value is reduced drastically. See, from 1.3 to it reduced to 0.4. Okay, this is the, we can say it is a very good application of metamaterial for human body to reduce the SAR. So this is another body antenna. I have taken numerical values. So this is a flat without no metasurface, metamaterial. This also bending in X direction without metamaterial, bending in Y direction without metamaterial. This is a flat condition with metamaterial. So when you compare, so the last 3 are with metamaterial, the first 3 are without metamaterials. So when you compare this two, the first and the third column, see here reflection coefficient is improved. So minus 24 to minus 26. Bandwidth, it is almost normally remains same. Though I showed in the previous diagram, though there is a shift in the central frequency, the bandwidth almost remains same. Here 2.26, it is 2.27. See now coming to this SAR, see the flat. See flat NMS means without any bending. They're not bending the antenna, they're keeping the antenna straight or flat condition. Here it is 2.53, it is not at all acceptable. It's not an acceptable range. Acceptable range is only 1.6. But here we got 2.5. So after applying this metamaterial, it reduced to 1.52. So lesser than 1.56. Still we made some arrangements and brought it down. Now similarly take this bending cases. When you bend the antenna, flexible antenna in X direction or Y direction. So here it is 1.37, here it is 0.7. Here it is 1.7, it brought down to 0.5. So this application of metamaterial in this kind of antenna, we analyzed and we came to know that there is a drastic reduction in the SAR. Okay, then we have taken the Fanda model and we placed the antenna in different positions, hand, chest and thigh, and we have analyzed the field analysis. In the 3D pattern, we use HFSS software. There is a provision is there. We place the antenna and we have analyzed this. Okay, this I have come to the end of the antenna. I have taken some examples what we have done in the lab and by the application of metamaterial, how this SAR is getting reduced. The second application is clocking. See, clocking is now people are working on this clocking. That is, when object is there, we have to hide the object. It is mainly used in the defense. So suppose an aircraft is crossing our area, our country, our radar must be able to capture at what speed where it is moving. Now the technology has improved that the aircraft can hide itself that nothing is there. Now our radar cannot be able to identify whether the craft is there or not. Okay. The identification is based on the visibility. When you take the visibility, say the diagram says there are two categories. One on the line, that is the light waves, other is on the EM, microwave frequencies or electromagnetic signals. See, how are the human eyes able to detect the presence of an object? That is, when light falls on an object, few wavelengths of light reflected back and few will be observed. So whatever the reflected energy, reflected wave reflected back, that is detected by our eyes and we say this is this color. We are saying black color means the black color is alone reflected, remaining all colors are observed. Okay, this is the principle used in the light. In a similar way, when you take the microwave signals, the microwave frequency also, the radar, radar stands for radio detection and ranging, it transmits a signal in the space to find our position or to locate the object. So when the radar signal receives the reflected wave or reflected signal back, it can be able to identify the object. Okay, that is the visibility. Now, Here, RF invisibility. How to make the visible object into a invisible one. Okay, there are two methods. The first one is called as a stealth, the other one is called as a clocking. Okay, stealth means there are two structures. One is a geometry structure. Other one is a radio absorbing material. Okay, RAM stands for radio absorbing material. These two structures. By changing the absorbing material geometry of a stealth, or you can changing the absorbing material, you can make the object invisible. Other method is called as a clocking. So clocking is, there are three types. One is a scattering cancellation, coordinate transformation, and transmission line. So among these three, in the scattering cancellation, we are using clocking and metamaterials. So metamaterials are used in scattering cancellation, which is coming in clocking, which makes the submarines or aircraft to be invisible. Okay, first, what is stealth? Just I'll give the introduction about what is stealth. Since stealth, see here, this is a normal convention. You take an aircraft. Normal convention, this is a radar. Okay, when signal is transmitted, reflected. Based on that, you can identify there is an aircraft. Now, stealth aircraft, what happens is the structure is changed. The geometry of this location, it is changed. So it is difficult to identify the structure is changed. See here, you can get the reflected signals. Here there is no reflected signals, all are scattered. So the radar will not get any reflected, so it cannot able to identify, though there is an object, though there is an aircraft, the radar cannot able to identify, the object is invisible to radar. So this is the principle stealth. This is also used to make invisibility for hiding the objects. Okay, other one is called as a clocking. Okay, clocking, I said there are three methods in clocking. Okay, from this you can see the clocking is different from stealth technology. Okay, in stealth technology, waves are scattered. Okay, scattered in different directions from the so that it will not reach the detector. But in clocking, what happens? It will not scatter, but the object is protected. Okay, the object is covered or protected by some cover. For this protection or this cover, we are using the metamaterial. Okay, this is the shield, this is a clocking. We are comparing both. It is written back. Here, this object is covered by the metamaterial, so that when signal strikes the surface, it will not return back. It will come around. It will be protected, so it will not return back to the radars. So already I explained what is scattering. Based on the transformation, coordinate transformation technique also, you can able to protect it. Okay, this is a scattering cancellation technique. Okay, the object is, so here this object, it is protected by, so both waves are, so here the object, this direction, this one, here the clock, this direction, this, so both get cancelled. So this is called the scattering cancellation technique. So this is a coordinate transformation. So in this coordinate transformation also, when signal is, this is a normal one. Normally when signal is strike over the object, this is the radiation pattern. But in this coordinate system, the structure is getting changed. So it will be, the wave is returned. Okay, it's not reaching it. Okay, this is another method, transmission line clocking. So in the clocking, we saw three methods, but only one method we are using the metamaterial. Okay. So this is a H-shaped metamaterial clock. Okay, this clock is used to protect, or it is used to cover the object. It is used to cover the object. So here, So this is a structure. This is a unit cell structure as normal what we have done in the antenna. The same way here also unit cell is first taken. A unit cell is taken. Now this unit cell is first analyzed. Then the unit cell is placed over the object. The object may be aircraft or it may be a cylinder or anything. It is placed over the object. Then it is subject to the radiation. So what will happen is this object will absorb, it will not allow the signal to touch the body or object. Okay, this is a head-shaped material clock. It is used. It is a bottom view. So this is object. Normally the object for simulation they used to take a cylindrical shape. Okay, this is over the object. There is a furfore or it may be a roger. Then you have a unit cell. So now how this object is placed over this unit cell is placed over the object. See here, this is a repeated structure. See this, this is a one unit cell. This is a single unit cell. This single unit cell is repeatedly followed. Next is a RCS. See, RCS stands for radar cross section. Okay, the radar cross section here it must be less. Okay, that is it should not cover this. So when you compare before RCS, so before clocking how much is there, after clocking how much is there. So we will see the diagram. After clock this RCS is less, very less. Before clock it is little higher. It's only for the comparison purpose. Similarly, we have different kinds of metamaterial which is used for the clocking. Here it is a tripling metamaterial. Okay, since we have three rings for here also same thing. One unit cell is first designed. The designed unit cell is now placed over the object which is to be protected. So when radiation is made to fall on the object, the object will not be seen. It will become an invisible object to the radar. The same structure is given. So same thing. This is a cylindrical object. Over the object, we have placed the metamaterial of shield. So this is also another comparison of this with clock and without clock. So as a conclusion, so we learned or we discussed about what is metamaterial. So metamaterial is not a natural material. It is an artificial material, but it is derived from the natural element. From this, you can change the characters. When you're changing the character, the material may become only mu negative or mu epsilon negative or both negative. When you want to use the material as the metamaterial, both the characters must be negative. So we'll discuss about how the antennas, especially in the medical antennas, how the metamaterial finds applications. The second application is clocking. The clocking also, metamaterial is used. So one more, if you're interested in the preparation of flexible substrate, I'll go. Otherwise, we can go for the question answer sessions. Hello, sir.
Ma'am, we shall continue with the flexible structures also, ma'am.
That is a substrate preparation. Huh?
Yes, ma'am.
Hello.
Ma'am.
Okay, sir.
Please continue.
Yes, sir. Okay. So this is a PDMS preparation. Okay, it is used for a flexible substrate. Normally, we used to buy the substrate in the shops. For it is readily available. Over the substrate, we will make. Okay, we will place our antennas, our radiating elements. Then we'll take the measurements. That's a rigid. That's a normal thing. Here we have to prepare the substrate itself. Okay, for the preparation, we have to buy the chemical called Silgod. Okay, the PDMS, it is the chemical based. It's a chemical based. It is a polydimethyl siloxane. Those who want to do it, please note it down. It is a polydimethyl siloxane. Its cost is around 8,000. Okay, but you can make plenty of substrate with this. Okay, you take a substrate and you have impurities. Okay, here now people are working on different kinds of impurities. It is not needed, you have to follow the same impurities. Based on the impurity, your dielectric constant will change. Okay, now people are, for this COVID, the people are working on mask, okay, nano mask. So here they are using the nanomaterials. So nanomaterial, now we can take, based on the requirement, they can take any ratio. Okay, I have taken 1:10. Okay, this impurity is added with the this Silgod, and both are mixed together. So this is a weighing machine to take the proper ratio of these two. So these are mixed together. So you have to stir it together in a bowl or something. After that, when you are stirring these two, see in the diagram itself, you can see there are some bubbles. Okay, you can avoid the bubbles. Okay, so yeah, you can put the stirrer and you can put it for some time. So what will happen when it is stirring properly, the bubbles will be removed. Okay, you can keep it for 1 hour or 15 minutes. Okay, once the bubbles are removed, okay, if bubbles are there, then you will not get a proper substrate. Okay, when bubbles are removed, so based on the thickness. So suppose they want a substrate of 1 mm thickness. You have to create a glass like vessel, small, not vessel, glass tray. Glass tray, it is, you can make when many glass shops in Coimbatore itself, there are many glass shops are there. If you give the dimensions of how many width, length we want it for glass substrate, they will give. You have to get the glass substrate according to your measurements. Then you have to pour this Silgod into that glass and keep it inside the oven for 12 hours or 24 hours. Suppose if you don't have the oven also, you can try. You can keep it outside in normal temperature, but the curing time, it will take more. Okay, when you cure it, after 12 hours, if you take it, you can feel it, you can see this is substrate. This is the PDMS substrate, over which now you can able to place the substrate, this radiating element. Okay, radiating element, and it will become the flexible. So now we can bend at any degree, it will not break. I'll show the antenna what we prepared. So these all are the PDMS based antennas. This is also so this is the PDMS over which we have placed it. So we can bend it any angle. It shall not create any problem. Hello, sir. Any doubts? Alan, sir?
Ma'am, thank you for the nice presentation, ma'am. Ma'am, we have few questions, ma'am. I will ask you one by one, ma'am.
Okay, sir. Okay.
Ma'am, how to calculate the radiation distance of the antenna, ma'am?
Hello?
Ma'am, how to calculate the radiation distance of the antenna, ma'am?
Radiation distance.
Yes, ma'am.
It's on which point of view, sir?
No idea, ma'am.
The radiation distance means from the simulation?
Yes, from the simulation perspective.
So I have not come across this radiation distance measurement.
Okay, ma'am. I will go to the next question, ma'am. Can you suggest any fabrication units in India for metamaterial design, ma'am?
So metamaterial, when you are going for flexible, we have to design. Because there is no standard design.
Okay, ma'am.
See, for each application, the specifications, everything will be different. Okay, see, when I showed the first, when we fabricated for reconfigurable antenna, the metamaterial structure character is different. When you go for flexible antenna, here the metamaterial, this is different. Also, you can use the metamaterial for absorber or you can use it for reflector. When you use for absorber as energy harvesting, you can connect the metamaterial with the energy source and you can, like the solar cell, you can save the energy. So I think there is no standard company or standard unit. We have designed our own substrate and own structures.
So if we have a nano structure lab, then we can do, right now.
Not needed. We are doing in electronics lab only.
Oh, okay.
Because many people in electronics field are unaware of this. They're thinking that this belongs to chemistry and nano department. Actually, only the chemical part thing we have to have, must have the basic knowledge. So actually, in our university, the chemical and nano people are coming for us for preparing the PDMS. Okay, they are good in nanoparticles and chemical, but in nanoelectronics, I don't think they have the facility of this. They may have, but we are doing in our labs.
Okay, madam, how to calculate the specific absorption rate?
SAR, sir?
SAR.
SAR, yeah. So in the simulation, we can make it. In the simulation, okay, once the antenna is designed, we have to create the phantom model. Where, in which position we have to place the antenna, we have to keep. Then we can go for the SAR analysis. In HFSS tool, there is a provision for using the SAR analysis. We can go. This is for the simulation tool. But as when you're going for measurement, this is not sufficient. Okay, we have to go for liquid phantom model. That facility is not available much. In Tamil Nadu, we have this facility only in Madras IIT. We discussed that there also, if you provide such liquid model, they may help us, sir. Otherwise, in simulation alone, we can take the SAR parameters, SAR analysis. But real-time analysis, once we design the antenna, yes, sir.
SAR, after fabricating your metamaterial antenna, you have simulated and got the results, and you have used the phantom. The phantom which is available in the simulator itself, and you have taken the results. Suppose you want to I want to measure the SAR of specific absorption range of the electromagnetic signals which are entering inside the body. Do you have facilities? You told that it is available.
Yes, no, sir. No. IIT Madras only we have. We try to take the real time, but as per our design, it is not possible. We tried North India, some states, they have the facilities, but we have to do it. We didn't go for that level. We have completed only the simulation part. The real time part, here the facilities are very less.
The SAR value should be as low as possible for protecting the body from unwanted electromagnetic waves entering into our body. Is it so?
Yes, sir. Yes, sir.
Yes.
So when you take any mobile, you can check. They have to give what is the SAR value. If you put #1 to 4 and check, they will give. They have to give. They will give the mobile phone what is the SAR value. SAR value must be less than 1.6. Otherwise, country won't permit to use the mobile.
Yes, thank you, madam. Thank you. I got enlightened by your metamaterial introduction to metamaterials and how it can be used in the antenna. So, what is the purpose of using metamaterial for fabricating the antenna?
So that's what, sir. There are two applications. The first one is you can use it for transmitting. See, when radiation is coming towards the antenna, you are protecting your body and you are returning back the radiations. So the gain will be increasing. That is one reason. We can improve the gain of the antenna.
Okay.
Second thing is, you can protect the backward, return,
Yeah.
that is the radiation towards the body. This is one application. Second application is, you can improve the energy absorption rate. If you connect some battery or something towards the metamaterial, whatever the energy is absorbed by the metamaterial can be saved as a solar cell. So both applications we can use it.
Okay. Thank you, madam. Thank you.
Thank you, sir.
Ma'am, we have 2 more questions, ma'am.
Yes, sir.
Ma'am, what is the dielectric constant of jeans material?
1.44, sir. We got 1.44.
Okay, ma'am. Ma'am, one more question, ma'am. Ma'am, in third quadrant, you said it is metamaterials.
Yes.
But the thin wire and SRR are said to be metamaterial is in second and fourth quadrant. Why so, ma'am?
So, no. They are not metamaterial. One property may be negative. Okay. Now, if you make this, as I said, if you make the LC parameters changes, we made some more changes in the structure. If you are able to make both this negative, then only that will be called as metamaterial. Otherwise, they are called as a single-ended material. Only one parameter alone be negative.
Okay, ma'am. Next question, ma'am. Ma'am, I want to know how to design the unit cell of metamaterial, whether there is any design equation related to resonant frequency of the antenna, and also how can I choose the shape of this metamaterial structure, since there are many shapes reported in many journals. Kindly address.
Yes, sir. So there are different shapes, different structures are there. As a beginner, you can start with a simple structure. Simple structure of double-ended square or double-ended circular. So creating one structure to test the structure by using unit cell analysis and prove that it is a metamaterial, then the same structure has to be repeated. That's all.
Next question, ma'am.
Okay, sir. When you're going for complex structure, it will be good. Yes, a beginner you can start.
Ma'am, design equation, how to design the unit cell of metamaterial? Is there any
Design equation, normal antenna equation, cell and width, you can use it, or by using trial and error method as we used in software, that is also you can follow.
Okay, so later you have to. Okay, later you have to show that this is a metamaterial structure. It's exhibiting negative permeability and permittivity. That's
yes, sir.
At the end you have to show that one, na?
Yeah, if a material shows both mu and epsilon are negative, that's a metamaterial.
Okay, thank you.
Thank you, sir.
Ma'am, next question, ma'am.
Okay, sir.
Can you give the journal name in which your presentation is there published?
Okay, sir. So I'll mail you whatever I have presented in the paper, in this thing, everything we have done it, all are published in scientific journals. I'll give the list, sir. You give it in the next session. Before the next session, I'll give it to you. I'll send it to your mails.
We will mail them.
Otherwise,
okay, sir. Is it possible to use metamaterial in implantable antenna?
Yes, sir. Yes, sir. You can use it. Implantable also we tried. We tried on work in implantable antenna, but there is a limitation. As this we were unable to test it properly because it is implantable. But simulation part we have done it.
Okay, ma'am. One more question, ma'am. Where can we purchase the pin diode for fabricating prototype model?
Yes, sir, that's an issue. We ordered States and we got it. We imported from States, United States. Actually, it is very cheap only. Very cheap, but we have to purchase 100 numbers. 100 numbers. I think here also available, but our specification we purchased, imported from States.
Ma'am, there are some more questions in the chat window, ma'am. I will ask you. How can I do the mathematical calculation for single unit cell? Whether there is any standard books available for that?
Sir, first you have to design the antenna. As I shown the formulas and everything, you have to calculate S11 and S21. Then put it in the formulas, then you can check it.
Okay, ma'am.
That's a MATLAB coding is there.
Okay.
Yes.
The next question, ma'am. How to calculate the number of structures in a cell? Whether there is any mathematical formula for that?
So we have not used, based on the size of the strip, we placed it. Yes, the size of the substrate, we place how much is adequate to fix. Based on that, we fix.
Okay, ma'am. In metamaterial, can we reduce the back lobe radiation?
Yes, sir. That's what. So back lobe is a the return loss, reverse, right? That can be shown the diagram. That is also there. You can make the back lobe and energy is converted into forward and increase the gain. Can improve the gain.
Okay, thank you, ma'am. Any more questions from the participants? I think it's a very good session, ma'am. Thank you so much for that information, ma'am. Now and there we will hear about the metamaterials, but don't know what is metamaterial. We only know what the structure is. Thanks for explaining the basics of metamaterials and the applications. What you have explained is very informative, ma'am. Thank you so much, ma'am. Thanks for the presentation.
Thank you so much for giving me the opportunity, sir. I would like to thank all the participants for listening the session, though it's a tough time after lunchtime. Thank you very much for listening. Thank you.
Thank you, ma'am. Now we shall start with the final session of our seminar. That is 5G antenna. The 5G antenna session is going to be handled by Mr. Venkatesh Dayanidhi. He is presently the faculty in ECE department of PSG Institute of Technology and Applied Research, Coimbatore. He is very fond of electromagnetic fields, signal systems, transmission lines, and RF and microwave engineering. He completed his bachelor's in St. Xavier's Catholic College of Engineering, Nagarkoil in 2004. After graduating, he worked as customer support engineer in VA Microsystems in Chennai. Then he worked as a lecturer in Muttayamal Engineering College, Rasipuram. Then he completed ME Wireless Technologies from Tyagarajar College of Engineering, Madurai in 2009. Then he joined KSR College of Technology as lecturer in Department of ECE. Later, he joined as Executive Engineer RF Design in TVS Interconnect Systems, Madurai from April 2010 to December 2011. From January 2012 onwards, he worked as assistant professor in Dr. Mahalingam College of Engineering and Technology until June 2016. From July 2016 onwards, he is working as assistant professor, senior grade in PSG Institute of Technology and Applied Research, Coimbatore. He is a man with very good passion in RF and engineering. We are proud to have you here, sir. Please start the section, sir.
Thank you, Alan. Thank you for your kind words. I'll just start.